All right, welcome. So in this video, I actually want to spend a little more time, a little extra time, talking about summations. We introduced them in the last video. So maybe as a side, I'm going to talk a little bit about them and show how the proof technique of induction that we've been using to prove our algorithms correct in some previous videos can also be used to prove that a particular summation has a particular closed form for summations that are maybe not straightforward and simple for us to immediately solve. So let's actually dive into that. And so I want to maybe expand a little bit on the series we looked at last day. All of the ones we looked at in the last video all had a term that we're summing over here that did not depend on the index I. And so I wanted to create our first and most sort of common and well-known example of this, which is where we just are summing the numbers between two bounds, the lower bound here 1 and n. So this is just a simple problem of adding all the numbers together between 1 and n, which as an arithmetic problem is sort of a simple make work problem that you might have in sort of grade school to practice your addition, but might also be, say, a step in a program, or as is more likely in computer science, is going to express the runtime of, say, a looping structure that changes over time. Now, when I say changes over time, what do I mean here? Well, if this sum were to express the runtime of a loop, what it means is that the cost of the loop increases every time we iterate. Now, this might happen if, for instance, we're doing something to a list and the list keeps getting bigger every time we do that. So maybe adding an element to a list, and every time we have to maybe read the whole list when we do it or something like that, we might get a pattern that looks like this. Starting with an empty list, we only have to do one operation, then maybe two, and so on, until maybe the last time we do it, we have to do an operation. So this could very well and very easily represent the runtime of some loop. And we might encounter that in some future algorithms that show up down the road here. So my goal here is then to figure out what is this sum equal to. This form doesn't really tell me what it's equal to because I need to know what n is if I want to fill in all the internal values. And then even if I do know what n is, there's a lot of arithmetic I need to do to figure that out unless I know what we'll call a closed form expression or a formula that tells us what this is equal to. Some of you might already know what this is equal to if you've encountered these types of sums elsewhere before. Okay, so maybe we'll just go straight spoilers here. If you know what it's equal to, here's the formula that it is equal to. If we add up all of the numbers between 1 and n, we get n times n plus 1 all divided by 2. Now, how do you know that? How do you know that? Maybe you already know that. Maybe you know that because you just have it scribbled on your practice sheet on the side, and sometimes that's a good way to do that. Now, another way to have it is maybe just, well, I've worked with it enough that I've got it burned into my brain. But the way that I burn it into my brain with most of the mathematical things is I'm not really great at memorizing something for the sake of memorizing it. I want to know why it's that way or how it works that way. That's how my brain categorizes things. So I don't really remember the formula. I remember how to get the formula if I've forgotten it. And so the way I do that is actually by remembering a proof of the formula. And usually it's not the whole proof. I don't memorize the proof. I just understand how the pieces go together to get where I'm going. And there are a couple cool and interesting ways that we can prove this particular theorem. And I'm going to go through a couple of them here today because I find them kind of elegant and fun. And so I want to share them with you. So the first one I'm going to do is I'm going to just practice induction. We've been working with induction. Induction is a very powerful and important mathematical tool, so that's why I want to practice it, but unfortunately it can sometimes be boring. So this, out of the 3 proofs I'm going to do for this formula here, I find it to be the most mechanical, the most sort of mathematical and the least interesting and fun. But for our purposes, it's going to be the best practice for doing induction proofs in the future. Okay, so that'll be the first one. Then I'm going to look at another proof. This is a proof due to a mathematician named Friedrich Gauss, who is a very famous mathematician from the 1800s. And I'll tell you a little bit about his proof. He's got a pretty cool and clever one, and the other cool, clever part about it is that he came up with it when he was, I believe, 10 or 11. And then finally, I'm going to do a proof. This might be my favorite proof because it's just with a picture, and that's what how the Greeks like to do things. The Greeks, Pythagoras and so on, these old Greek mathematicians really like to think about these different kinds of puzzles and problems, but they focused a lot on geometry and how shapes work specifically in 2 and 3 dimensions. And so they came up with a real cool proof of this sum. They probably weren't worried about the sum, they might be, but they came up with a cool proof using geometry, and I'll share that one as well. But so let's start maybe with, as I mentioned, maybe the more boring one, the proof by induction. Okay, so let's say, okay, proof by induction, how does that work? Now remember, the way that induction works is we're going to have sort of 2 steps, the base and the inductive step, the base case and the inductive case. And the way those work is the base case, we're going to prove it true for one case, usually the starting case that we want to prove it true for. And then we will use the inductive case to say that if it worked for the last one, n, it will work for the next one, n plus 1. Okay, so let's see how that works here. So here I'm going to use induction on n as my n changes. So let's pick a base case. Now my base case here, I could actually pick one of 2 possibilities here. I picked n equals 1, but I might have also chosen n equals 0. Now n equals 0, what is the sum of all the numbers between 1 and 0 is actually 0. There's nothing there, and that relies on a sort of a technicality or a special case there, that if we're not familiar with it, that proof might be not very easy to do. But if we do rely on that one, it actually gets very easy, because if the sum itself is 0, it's very easy to see that 0 times whatever else is here is 0. So we would get 0 on both sides. However, the proof I've chosen to do here, I'm going to start at 1 instead, and that makes just as much sense. So let's see what happens if we took all the numbers from 1 to 1 and we add them all up. Well, they just add up to 1. That makes sense, right? Okay. Now for our base case, we just need to check to make sure that the left-hand side is equal to the right-hand side. So let's do the same thing. Plug n in for the right-hand side. So we get 1 times 1 plus 1, all divided by 2. Well, that gives us 2 over 2, which is 1. And here we just check. 1, is that equal to 1? Yes, check. So often, as I mentioned before, I think, in my base cases, sometimes the base case is so straightforward and simple, we're really just checking if something's true more than proving it's true. That's how simple it is, that I sometimes just put a big check mark after it. Like, that's more a reminder to myself, hey, you're done. You checked that it was correct, so you're done. You can move on. You can go to the next step now. So here we verified the left-hand side is equal to the right-hand side. 1 equals 1. We don't need any saying here, and since 1 equals 1, we're done. So I put that check mark in there basically to stand in place of the, well, we all can see that 1 equals 1. Okay, so let's move on to the next step then, which is the inductive case. The inductive step, or the inductive case, where we again want to assume it's true for n and then argue it's true for the next case, n plus 1. All right, so to start that off, we need the actual hypothesis. Assuming it's true for n plus 1, what do we need to prove? Well, I've gotten that sort of stated down here. I've taken what we've got up above, which is our statement in terms of n, and I've plugged in n plus 1 into all my occurrences of n to see what it is that I'm supposed to show in this step. Remember, we are assuming it's true for n, but we need to show it's true for n plus 1. So what do we need to show it's true? Well, here, again, I've just replaced my n's with n plus 1s, so my sum is now changed. And here, well, I put around some extra brackets around it, we get n plus 1 times n plus 2 all divided by 2. Okay, so this is what I need to prove. So I'm going to start with the left-hand side, and I know I'm done when I get to the right-hand side. Okay, so let's start that. And so on our next step here, what I'm going to do is I'm going to bring down my left-hand side. That's the I equals 1 to n plus 1 of I. And then I'm going to try, what I'm going to realize here is that this sum, I can rewrite it so that it has this form up above. This is the form I want to get to, because if I can get my sum to look like this, I know by my assumption and my inductive hypothesis that I'll be able to replace that sum with the right-hand side. So what I'm doing here is I'm going to break off the last term. The last term in this sum is n plus 1. So I'm breaking it off and placing it first. And all the other elements of the sum, we can just write like this: I equal 1 to n of I. Okay, we can see that. Now this is of this form. So now what I do in the next step is apply the inductive hypothesis and replace this sum with what's written on the right-hand side. Okay, so I've replaced this sum with what we know it to be already, with what's on the right-hand side. Now, all that I have left really is algebra to try and argue that this thing that I've got here is actually this thing. So how can I do that? What do you think the next step might be? Well, here I've got a fraction. If I want to add these together, blend these together, I need to make the fractions be in the same terms. So I have the same denominator. So I'll multiply this left-hand side by 2 to be able to do that. So I'm going to get 2 times n plus 1 plus n times n plus 1. Now notice, look here. N plus 1, using my normal sort of factoring rules, I can factor the n plus 1 out of these two terms. And what does it give me? It gives me an n plus 2 term. And hey, that's what I was looking for. I guess I got them in the wrong order here, but that's exactly what I was looking for. So we've shown the left-hand side equals the right-hand side. We're done the inductive step. So by induction, we've shown the formula that we want. Okay, now again, this is using induction. Sometimes there's sort of the magic of induction. We've sort of assumed here what we were trying to prove and showed that that does indeed give us what we want. Now, sometimes we can think that this is begging the question, but here we're assuming what we're trying to prove in order to prove something completely different, something for n plus 1. Okay, if we were assuming this was true for n and then just proving n, that would indeed be begging the question. But in this case, we've completed this inductive proof. Now, again, I mentioned this, or I include this as practice to practice induction, okay? Because you might now encounter a different sum with a different term. Instead of I, maybe 2 to the I. That's something that we'll look at in a second here. And that one's going to have a different formula that you might want to prove correct. So as you encounter different formula, you might want to prove them correct, and induction is probably the tool you want to use because it has the power to handle all of these. Okay, let's continue. Now this next proof here, this is the one I mentioned, is due to Friedrich Gauss. And so I'm actually going to do this one. I don't need to draw a picture for this one, but I do want to sort of share a little bit how his reasoning went. So let's say we're Friedrich Gauss. Now, first of all, Gauss, as I mentioned, he did this when he was in grade school. He was about 10 or 11, if I remember this story properly. And maybe I should be 100% clear, or a big caveat here. I heard this story from one of my university professors, and now I share it as a university professor as though it is the truth. It may be completely a lie made up to me by my professor. So I'll throw my professor under the bus if this is a complete lie. But at the moment, I'm gonna say that it is true. Now, Gauss was a student, I believe, in Germany, and at the time in grade school, he was learning his arithmetic, and he was being taught by, as was the common at the time, usually a priest or a father or some kind of member of the clergy. And this particular member also was fond of the drink, and so enjoyed to have a goblet or two of wine or ale during the day. And so a common thing that this particular mentor or teacher would do is ahead of the class, before the class, he would set all the students with their slates. You know, instead of a paper, they'd have a slate and some chalk, and he would assign them a arithmetic task. And he would usually assign them a hard arithmetic task, and one that would take a number of hours, so that he could go visit the neighboring pub, have a couple pints, and then come back afterwards and check on the work. Now, in this particular day, the teacher assigned the problem of adding all the numbers together between 1 and 100. So 1 plus 2 plus 3 plus 2, plus, and I'm going to, you know, add the last couple here as well for a reason that will become clear in a second. So he said, okay, Gauss and all the other students, add all the numbers between 1 and 100, and at the end of today, tell me what, you know, what the numbers, what it adds up to. And of course, this seems like a lot of work. You probably have to do 100 additions if you don't know any better. And if you're just, you know, a 10-year or 11-year-old, you've just learned how to add, that's going to take you a long time, probably a long time. So, you know, the teacher, quite proud, says, okay, haha, you know, rubs his belly off to the pub. But before he exits the room, the smart kid in the class, Gauss, puts his hand up and says, "Oh, I think I know what the answer is." So it's this. Now you can imagine the anger of the teacher, who he himself does not know what the answer of 1 plus 2 plus 3 up to 100 is, because he was about to go to the pub and over a couple pints on his own slate go through 100 additions, hopefully quicker than the students, and come up with the answer himself. So he did not know what the answer was. So how did Gauss come up with the answer in just a few seconds? Okay, so what was the genius that Gauss noticed? Well, here's the cool part, and this is the part I love. This is maybe not my favorite proof of this one, but it's still very clever. He noticed that if he added the first number to the last number, 1 and 100, he gets 101. And if you add the next two together, 2 plus 99, you get 101. And if you add 3 plus 98 together, you get 101. Now, how did you do this? Well, you did this by pairing numbers up. So how many pairs would there be? Well, there would be 100 divided by 2 pairs, which is 50 pairs. And if each one adds up to 101, then the total would be 50-50. Okay, now let's check. Is he right? Because how did he come up with this, or how is this indeed correct? Well, let's say that he wasn't asked to add up all the numbers from 1 to 100. He was asked to add them up from 1 to n minus 1, or n, sorry, n minus 1 and n minus 2 I wrote in there. Now what would it add up to? Well, the first one and the last one, if we add them together, would be n plus 1. The second one and the second last one, if we add them together, also n plus 1. So how many such pairs are there? Well, there would be n over 2 pairs, which is exactly the formula that we had come up with earlier, that we had proven with induction. So indeed, see, there's my check mark confirming I've got it right. Indeed, it looks like Gauss has indeed got it correct. So I've got that same argument here. Just very simply, if you add the first two together, or the first and the last element, you get plus 1. This is true for the second and the second last. We compare all elements in this way to get the sum n plus 1. How many such pairs are there? There will be n over 2 such pairs, so we get this, indeed, this formula that we expected. So cool proof. Okay, last proof. The last proof I want to do for this particular series, I mentioned, has to do with a proof by picture, a geometric proof that is due to the Greeks. The ancient Greeks, I should say, not the modern Greeks, the ancient Greeks, although there's probably some modern Greeks who know this proof too. In this case, I've decided to limit my proof to just n equals 4 for simplicity. And I guess in this sense, that's a limitation on my picture proof. You might believe it for 4, but you might not believe it for 5 or 10. If that's the case, I will refer you to my inductive proof that we've already taken a look at. Okay, so the first thing I want you to do is just take a look at this shape I've drawn here, and you'll notice that this shape, the area of this shape, if each square has area 1, then the area of this shape is the area of 1 plus 2 plus 3 plus 4, because we have 4 different shapes here of size of towers, if you want, 1, 2, 3, 4, or levels 1, 2, 3, 4. This shape is the sum of 1 to 4, and of course we could expand on this, and hopefully all of our internal mathematical processors can expand on this and see that indeed if we expanded this to 10 or 100, we'd have the same looking shape. It would just have more levels or rows or columns on it, whichever way you're thinking of it. Now, what the Greeks thought and what they realized is if you flip this shape, if you rotate it, you can add it into the shape that you've just created like this, and you can stick them together and make a rectangle. Now, the original shape is not the type of shape we know the area of necessarily, but the rectangle, this is a shape that is easy to calculate the area of, and again, very well known to the Greeks, width times height, fairly easy. Now, what is the width and the height in this particular rectangle? Well, the width here, if we look along the bottom here, is 4 plus 1, 5. But the height, at least the way we've drawn it here, remains 4. We could have plugged it on the top here and switched it around. But regardless of how we drew this rectangle, one of the dimensions is going to be 5 and the other is 4. Or, translating that into n terms, one will be n and the other will be n plus 1. Okay, so this rectangle has dimensions n by n plus 1. So we know that its area must be n times n plus 1. That's the formula for area. Now, of course, there are 2 of these shapes in here, so that area divided by 2 must be the area of one of those original shapes. And so that's how we get there as well. So again, we've got now 3 different proofs of how we can get this formula. Now, hopefully, if some brains are like mine and some are not, and I've heard, at least in discussions of cognitive science, some people call my brain a non-labeler brain. And what that means is I'm not great at remembering names. I'm not good at remembering dates. I'm good at remembering ideas or concepts or things. And so I'm not good at memorizing this formula just for the sake of memorizing the symbols. I'm good at memorizing or remembering the reason why these symbols are the way they are. So I can never really remember the formula. I remember the proof. And I remember for a couple of my math tests back when I was in college that I would forget a formula and I'd have to derive it on the page there or something like that so I could apply it. And that's just the way my brain works. Now, there's a whole bunch of other people out there in the world who are just labeler brains, which is a lot of people that are good at memorizing labels and names, in which case, if you need to remember this theorem, you probably just remember it. You write it down, remember it a handful of times until it burns into your brain. But if you're like me and you're not great at memorizing, then what I recommend doing is remembering a story like this. Remember about Gauss and his mathematics teacher who liked to drink pints of beer. Or remember the Greeks and how they like to draw pictures and how these pictures help you understand this formula. And if you can remember those stories, again, that's how my brain works a little better, then you can track your way back to the formula that you're looking for. So I included these 3 proofs as a way to see 3 different ways to demonstrate the same mathematical fact using different mathematical principles, showing that there's not just one proof for any particular theorem, but also to highlight that there are different ways to judge what a proof is. And maybe that's something that I do want to bring up here, which is this idea of elegance. We'll often describe a proof as an elegant proof. Okay, so here we might say, which of these proofs is best? Now, best isn't a great word because it's very vague. So which is the more elegant, or which one is your favorite? And which one is your favorite is purely subjective. It's up to you. Maybe you love induction, then go ahead. Maybe induction's your favorite. That's up to you. And all the power to you. I mentioned I really like the geometric proof, but I also think Gauss's proof is very clever and I like it, okay? And usually that's some of the things that we look for in a proof. Is it clever? But also, is it easy to understand? Sometimes being clever is not necessarily easy to understand, right? Is it easy to understand? Is it clever? Is it concise? Meaning, is it short enough? Does it have only the relevant information? Is it precise? Is it got all the details that are necessary? Is it not overly vague in certain areas? Sometimes proofs can be overly vague when you assume your reader is, as clever as you are and they can fill in the bits. That doesn't make for a very good proof. What makes for a very good proof is one that's clear and easy to understand and easy to follow, even if your audience is not being super clever, okay? Maybe so they can follow how you're being clever in the proof. So these are some measurements. I haven't mentioned all of these here on the slide, but sometimes things that we're looking for, the things that I've highlighted here is its length and its simplicity. I guess things I didn't highlight that is maybe more important is, are the proofs correct? That's first. If it's not correct, we just throw it out, right? That's not very good. So is it sound and valid? If it is, indeed, usually validity is more important than soundness. If it's invalid, we just throw it out altogether. If it's not sound, meaning some of its premises might be false, well, if some of the premises are known to be false, then it's not very useful proof. But if some of the premises are not known to be true or false, we don't know, then we sometimes still like proofs of that matter, okay? But as I mentioned, how efficient the proof is, how good it is after we know it's correct, depends on how easy it is to understand and how maybe short it is to write down. When we have these nice proofs that we like, we use the word elegant, which again is a subjective term. It doesn't really have an objective definition to it, but we usually prefer elegant proofs to inelegant ones. Okay, I want to conclude this video on summation and induction with another proof by induction, which again might not be the most exciting of the proofs, but we're trying to practice this proof technique so that we can apply it for trickier versions of these summations that don't lend themselves as easily to very simple geometric arguments or type of clever argument like Gauss. So here's the next example, and I pull this one out because again I'm assuming a lot of my audience here are computer scientists, and so binary shows up a lot, and so powers of 2 show up a lot, so you might encounter something like this, which is the sum of all the powers of 2. And here I've deliberately started at 0 instead of 1, and that's because the first power of 2 is 1. And typically when we have mathematical formulas showing up of this form, we often start with 1, not 2. And so I started at 2 to the 0 equals 1. So this sum, again, we call this a geometric series instead of an arithmetic series. And it also has a closed form expression that you might know, which is just the next power of 2 up minus 1. And maybe I will do a quick, more elegant proof of this after we tackle it by induction. As I mentioned, practice by induction again. So let's do it by induction. And here, again, I've got it stated by induction. We're going to do induction on n. So what value of n should we choose to start with? Well, probably 0, okay, because 2 to the n, 2 to the 0 is the simplest to calculate. 2 to the 1 is not that hard to calculate either, but let's try it for 0. So let's again, what would the two sides of our formula be? 0 to 0 just means 2 to the 0 is just 1. The right-hand side would be 2 to the 0 plus 1, which is 2 minus 1. 2 minus 1 is also 1. Again, check mark. The base case is usually so simple and straightforward. We're just checking that left-hand side equals right-hand side. And if it does, we proceed. If it doesn't, we probably messed up somewhere. We're probably proving something that's not true, or we picked a bad base case. Okay, so let's move on to the inductive step. Base case pretty straightforward in this one. The inductive step, so we will assume what we're trying to prove here for n. Okay, but we will now try and prove it for n plus 1. So again, we're going to plug in n plus 1 for our n's here. Okay. So I've plugged in n plus 1 here. Where do I have it? So on the left-hand side, instead of this n here, I've got n plus 1. And I want to show what this one's going to be equal to. And I'm going to follow the same strategy we just followed for our previous inductive proof, which is I'm going to try and rewrite the sum in a way that it looks like this instead. And the way I'm going to do that is breaking off that last term. The last term in this sum will be 2 to the n plus 1. So I've broken it off here. And then I can rewrite the remaining terms as a sum still, but now just going from 0 to n, not including that last term which we broke off. Now, this sum, of course, we can replace rather using the inductive hypothesis. The purpose of rewriting it this way is so we can eliminate the sum and replace it with the right-hand side here. So I will now replace that with the right-hand side. So we've got the right-hand side here would be 2n plus 1 minus 1. So that's what I have here, 2 to the n plus 1 minus 1. And of course, we can maybe do a little algebra here. What happens when we add these two together? We get 2 times that. And of course, what happens when we multiply this by 2? We increment the exponent. So we get 2 to the n plus 2 minus 1. And of course, that's what the right-hand side would look like. If we plugged in n plus 1 for it, we would get 2 to the n plus 2 minus 1. So indeed, we got where we're trying to go here. We got what we're trying to prove. Okay. So again, we'll just conclude by saying that by induction, we have shown the theorem, proven the theorem that we want to prove. Okay, so I include that last proof here as, again, an extra practice in induction for this particular series, geometric series. And I might leave it as practice to do a couple other proofs of this, maybe a proof for 3 to the I, the sum of I equals 0 to n for 3 to the I. That would be a slightly different proof. Following the same strategy, you should be able to prove what it is equal to. Okay. Now, I did say maybe I will include one final proof here, a more elegant proof of that same formula. So let's go ahead and take a look at that. That same formula. Ooh, that's an awful looking sum sign. I equals 0 to n of 2 to the I. Now, the extra proof that I liked, well, this one I mentioned, let's write down what it's equal to. It's equal to 2 to the n plus 1, the next power up, whole thing minus 1. Now, one way I like to remember this, and this is helpful if you've been practicing your binary conversions, which of course are important if you're a computer scientist. So in binary, let's consider this number for a second. And I'm going to say, so this number here, if we consider it in place value form, we're going to see that this place value here is 2 to the 0. This is 2 to the 1. This is 2 to the 2. And let's say for the moment that this is 2 to the n. Dot, dot, dot. Then this number in binary, if we want to know what it's equal to, is actually equal to this sum, because it's 1 times the 2 to the 0's place plus 1 times the 2 to the 1st place, and so on. So this sum that we're trying to figure out here is actually this number in binary. So if we know what this number in binary is, we know what this sum is. So what is this number in binary? Well, actually, I don't know what this number is in binary, but follow with me a little trick. Let's say I did this. Let's say I added 1 to this number in binary. Then I'm going to get a bunch of carries until, and I'm going to have n plus 1 zeros here. Why? Because I had n plus 1 ones up above here, starting at 0 going to n. And they're all going to turn to zeros, and we're going to carry over with 1, 1. Well, this number here, we should know, this is easy. This is a power of 2, right? And it's a power of 2. Which power of 2 is it? It's going to be the next power of 2. 2 to the n plus 1. Okay, 2 to the n plus 1. But how did I get to this number? I got here by adding 1 to the number that I really wanted to know what it was. So the number that I wanted to know what it was must be 2 to the n plus 1 minus 1. And that's what we have here. So this elegant proof relies on knowing how binary works. So hopefully you've had practice with binary. But this is a second, I like to think, more elegant proof than the inductive proof. But again, the inductive proof is good practice, so that's why we've included it. Okay, that's all that I wanted to do in this video. So thanks a lot for watching, and we'll see you in that next video.